Often, rather than having a single differential equation, we have several, and they interact in a way that prevents them from being studied individually. In this video, we'll give a motivating example to demonstrate how this can happen. The example we'll look at is from epidemiology and is called the SIR model. It was introduced by Kermack and McKendrick in 1927 and has been hugely impactful. Even today, people continue to study variants of it. But the original model was simple enough to state. You have an outbreak of an infectious disease. This disease is non-fatal, and people eventually recover from it. It grants immunity so that people who have recovered do not become reinfected. This allows us to sort everyone into one of three categories. Susceptible people have not been infected but might be in the future. We keep track of the number of people in that category at time t as s of t. Infected people, these people will eventually recover. We call the number of people infected at time t I of t. And recovered people who are now immune to the disease, we'll call the number of people in this category R of t. And we now set up differential equations representing how each category changes with time. ds dt is negative because according to this model, people can leave category S and by becoming infected, but they can never return to it. Once infected people recover, they go into R, not S. Now, in particular, for someone to leave S, an infected person and a susceptible person have to meet. The number of such meetings that can occur is S times I. The constant B rolls together the probability of a meeting occurring and the probability that it results in infection. dr dt is positive. People entered the recovered state and then don't leave. The number of people who are recovering at a given time depends on the number of people who are infected. at that time. This K represents how quickly people usually recover. Now DT is the number of people who leave S minus the number of people who leave I to enter R. BSI minus KI. So consider this system. Imagine trying to solve this first differential equation. If the I weren't there, it would be easy, exponential. But the I is there. We have no hope of solving for this unknown variable as long as we have this second unknown function floating around. So to solve for S, we need to already know what I is. But S appears in this equation. So the precise same problem occurs. To solve for I, we need to already know what S is. And to solve for R, we need to already know what I is. In this video, we have seen how different variables can become entangled. In the SIR model, we cannot pick one of the three unknowns and start with it. To solve for any of the three variables, we have to already know another variable. Our only hope for dealing with such a situation is to discover some method that allows us to solve for multiple variables at once. Since we can't solve most individual differential equations, trying to solve systems of differential equations might seem like a hopeless task. And to a point it is. However, we will learn how to solve simple systems, and then we will see how those simple systems can be used to study more complicated systems, even if we can't actually solve them.